Okay, today we are doing chapter 9. This is arithmetic and geometric sequences, and they look scary. I hope they don't feel scary after we're done today. We'll start with something simple. Here's a sequence versus a series. If you have 1 and then 3 and then 5 and then 7, that's like one of the most simple sequence or series? The sequence. And if you think about it this way, like after you've recorded a whole bunch of Netflix and you put it in a package, they call it a what? A series. And that's a whole bunch of the sequence, except it's like they stop. They stop, and that series has like season 1, season 2, etc. Well, what if I say I want you to take those numbers, then they keep going forever, but I want you to just add it up from 1 to 25. That'd be the first 25 numbers in that series. Now, that would take you a long time. I'm not asking you to actually do that right now. I'm just saying that's the difference. A sequence versus a series. A sequence is just, this is a sequence. But when you actually tell people to add them all up from here to here, then you're giving them a series problem. All right, so have you ever been in a class where there's this kid who's the really annoying smart kid who just, like, he finishes things in 2 minutes and is like, I'm done, what do you want me to do? Or they're just so far above everybody else that we take this really hard test. They get the A, everybody else gets like C's, and the teacher says, well, some people got A's, so it obviously wasn't that hard. You know what I'm talking about? Okay, so there's a little kid named Friedrich Gauss, real person, true story. It's a German boy, and he was a little kid, and he was that kid who was just so smart, and his teacher was trying to keep him busy, so he said, all right, Friedrich, just go and add up the numbers from 1 to 100. He's expecting, okay, he's got this kid busy for like 20, 30 minutes. He's really smart. So, but Friedrich goes back to his desk and like writes a couple things down. He walks back up to the teacher and says, here's the answer. He's like, no. There's no way you could have added up the numbers from 1 to 100 that fast. And actually he had. So I want to see if you could be like Friedrich. Here's the numbers from 1 to 100, right? 1, 2, 3, ... I want to see if you can figure out how he did it. I know some of you already might know the punchline, and that's cool. If so, you should be able to know what the answer is. And if you want to stretch yourself, try adding the numbers from 1 to 200 if you already know how to do 1 to 100. All right? See if you can add up the numbers from 1 to 100, and I can do it in less than 30 seconds. So there's obviously some trick to it. See if you can figure it out. I'm going to give you a couple minutes to think. And I'm going to call on a random person, not just the 3 eager beavers who raise their hands. I want to see how many people think they have it, but then I'll call on a random person. Tell me anything you tried at least when I call on you. Okay. Checking on you now. How many do you think you have it? All right. It's 5 people. That's awesome. All right. I know one of you actually used the calculator. Tell me what you think. 4,950. Excellent try. Not correct. So all that proves is that it's easy to get lost when you're adding up 100 numbers on a calculator. So even that method is hard. What do you think the answer is back there? All right, good guess, but no. Now, if you tell me the answer, I want you to tell me why you think it is. Because obviously we can Google this sucker. It's not that hard to do. Yes? The answer is 5,050. I know you had it too. 5050. Okay, now how? Wait. How many of you think you know, after hearing that, you think you're onto it? 1, 2, 3, 4, 5, 6 people. All right. I'm going to start over here in the blue. Yeah. I mean, why is it 5,050? How did you do it?
The reason why it's 5,050 is because you have 100 numbers.
Agreed, there's 100 numbers. I'm going to keep going. I'm not going to write them all, but I'm going to write the ending. 9. Oh, wait. Okay. How do you know the average of the numbers, though? It is 50.5. Can't argue with that.
You know the average of the numbers because you take the average of the n2 numbers here and set with all the patterns.
Ooh, okay, wait. So you said the n2 numbers, 100 and a 1. There's 101.
Yeah,
And you average those two numbers. I like it. 99 and 2 also make 101. And every other combo like it would make 101. And you're saying you could just take that and saying the average of those two numbers is 50.5, because 101 divided by 2 is 50.5. And you times that by 100 terms, and that would get you 5050. Very nice. There's another way. You're not wrong. That was a good way. What do you think? 101. So he didn't ever use the number 101. No, wait, he did. He did 101 divided by 2 made 50.5. Okay, so you're going to use the number 101. What are you going to do with it?
101, and then, so that's if you get a pair.
Mm-hmm.
If you pair of 1 and 100, that's a pair of 101.
Mm-hmm.
And then 299, 101.
Mm-hmm.
Pairs, so you multiply by.
And you times it by 50. And that is 5,050. Another correct way. No wonder you guys are one of my best classes. Got a lot of good ideas there. Okay, so do you have to be expected to do that? Yep. So now add up the numbers from 1 to 200, knowing what you know. It's going to be just like this. Add up the numbers from 1 to 200. And you don't just double that, by the way. That doesn't work. Pause for a second when you give that a try. Okay, this time, how many of you have it? That's not everybody, so not everybody's caught on to what's going on here. If I'm going to end this time, it's going to end with 200 and then 199. So if you use the same system, it's 200 plus 1 is 201. And then how many pairs like that are we going to have? Yes, 100 of them. And that means we just times it by 100. And so then you move the decimal over a couple of spots. 201 with a couple extra zeros. And there you go, 20,100. Raise your hand if you had that one right. Cool. Okay. I don't think so. 101 averaged. 201 averaged would be 100 point. What would it be? 100.5. And then you times it by the whole thing. Okay. Interesting. Well, this is the way that most people describe it. I think your way is very similar. It's actually just done in a different order, because there's a divide by 2 in there, and there's a divide by 2 in this one, because we go there's half as many pairs, so we take 100 instead of 200. So there's a divide by 2 in ours. It's just done in a different order, but that's cool. Nobody's described it to me that way before. All right, so that's adding up a whole bunch of numbers. What do you have to do today? Well, that's not actually it. There's a whole bunch of other stuff you actually do before this. I just want to kind of show you where we're headed. But here's the stuff that you need to get, like in the middle of a sequence, 28, 31, 34, dot, 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 and there's stuff before it and stuff after it. Do you get I can pick any term and call it A sub, what do you think for any term? A sub n. A sub n. And then what's the term right in front of it called? And don't change the letter. A sub n minus 1. And do you remember last year we did u sub n and u sub n minus 1? You remember doing that in honors pre-calc? Or honors higher algebra, sorry. Well, this is a sub whatever. So if that's a sub n minus 1, what's this one? A sub n plus 1. And what do you call the very first one? The very first one in your series that I can't see on this screen, but it was way back here somewhere. A sub 0. We're using A's, not U's. So A sub 0 is the very first one. Do you remember, again, last year, that you didn't have to start with sub 0 as your first one? You could start with sub 1 if you wanted to. Or you could even start with U sub 2006 or whatever. Okay, so you could start with any number you wanted to. All right, so They do that too, except I'm just going to say it this way. That is the starting term unless they tell you otherwise. A sub 0. All right, next thing. When they're going up by the same thing each time, get that's called a common difference or a common ratio, and do you remember which one's which? If it goes up by 3 each time, that's called a common what? Difference, because if you subtracted the 2, that's called difference, then the difference would be 3. All right? What would it be if it was going up like this? 2, and then doubles to 4, and then doubles to 8, and then doubles to 16, dot, dot, dot. That's times 2. Times 2. That's called a common ratio. You are correct. All right. Next, I want you to think this through. What if I gave you that question that's doubling each time, right? And I said, what is the 50th term? I know you could use the OM method and just take a calculator and times it by 2 over and over and over and over and over again, finally get the answer. But if you want the 50th term, it'd be really nice to have a formula for that. I'll give you a hint. I'm going to ask you to figure out the formula, and it starts like this. A sub n, any term, is given by the first term, a sub 0, and then you got to do something to it. Try to figure out the formula that would work for anything, not just for 50. And if your formula really works, then the fourth term, if you stick it into your formula that you want the fourth term, it better give you 16. Otherwise, you must not be doing it right. Try to make me a formula that starts like that. And it'll use R for common ratio, or D for common difference, and N for the term that you want. I'll pause for a second while I give that a try. Times 2 to the R N. All right, let me double check you now. Is that what you said? Just make sure. Okay. So I'm going to try this. I'm going to try to find the fourth term, and it should come out to 16. So I'm going to put in a 4 here for my fourth term. And my R, my common ratio, is 2. And my A0 is 2. No, A sub 0 is not 1. The first term is a 2. Okay, so then that wasn't your formula, so let's try it again. To the n power. Are you getting closer? Not quite. Let me show you what happens. When I stick in a sub 0 is my first term, it's 2. Remember, a sub 0 is the first term unless they tell you otherwise. 2 is, that's supposed to be a variable. That's the R, the rate. So here's your formula actually. I'm going to back up one notch here. Let me pause for a second. So here's the proposed formula. A sub 0 times R to the n. And I'm going to stick in the numbers I know. Starting 2. R is 2. N is the fourth term, is 4. 2 times 2 to the fourth. That's 32. It's like 1 too big. This is really close to right. Yes? Finish it off. To the n minus 1 is correct. You finally tweaked it till it's perfect. That's it. Write that one down. That is the formula for finding the nth term in a geometric sequence. So if I really wanted the 50th term, would you please put in the numbers? I know you're going to have a power of something, because you won't be able to do it in your head. But put in the numbers to figure out what the 50th term would be then. Did you get 2 for your A0? Did you get 2 for your R? And did you get 50 for the term you want? So therefore, it's 2 times 2 to the 49th. Awesome. That's the answer. Okay. So that's for geometric. How about arithmetic? 1, add 4 is 5, add 4 is 9, dot, dot, dot. What if I want the 300th term of that? You're not going to do it 300 times, right? You're going to figure out a formula. Yes, sir. Now, start with a sub. There you go. Yup. Except there's no R in this. It's all right. It's all right. It's not R. It's something else. What is it? In this kind of problem, we don't have an R. We have a D times, what do you think? And minus 1 again. You got it right. Nice job. You better write that one down. I'll tell you it's right. Now I want you to prove it's actually right by finding not the 50th term. We'll just find the 4th term. You could have done it another way, so you'll be able to check yourself. What is the next term after this one? And make sure that this actually works. A sub 0, also known as 1, is what we started with. D, the difference is it's going up 4 each time. Plus 4, and then to get the next one, I'm going to have to add 4 one more time. Plus 4, it should be 13, and let's see if our formula spits that out. The difference is 4, and this is, we wanted the first, second, third, fourth term, so we go 1 plus 4 times 3, which is 12 plus 1, which is 13. Cool, it worked. All right, so that's the formula to find the nth term. This chapter is a formula-laden chapter. Once you have the formulas down, it's not that bad. We're going to be doing it, obviously, for a few days here before break, but then we'll finish it after break, and that'll be your last test to be on this stuff. What we're going to go to next is things like adding up like this. This is a big summation symbol, and it looks really intimidating and stuff. Would you say, let's say, n equals 0 to infinity? That means I want you to add up the things from 0 to infinity like that. Well, what are the first couple of them? Well, what did we say by saying this? What do you think we said to start with? This is an epsilon symbol. It's a Greek letter. Okay? So it's saying you want to go from 0 to infinity. So n is 0, so I'm going to stick in a 0 there. That's the first one you stick in. So what's 2 times 0? Plus 1. So 1 is the first thing in your sequence. Would you find me the next 3 things in that sequence? So basically it's saying start by sticking in 0 and keep going until infinity. Well, we're not going to do that, but we're going to go get the first 4. When you stuck in the next thing after 0, which is 1, you stick a 1. 2 times 1 is 2, plus 1 is 3. Did you get 3? Cool. What's the next thing? Stick in a 2. 2 times 2 is 4, plus 1 is 5. And look at that. I have just showed you the fancy way to write the odd numbers. You know what I'm saying? All right. Now, if you actually had to do this summation symbol, it would mean you actually have to add up all the numbers. What do you think the answer would be? Infinity. Good. Now, here's one that's going to stretch your mind a little bit more. What if I have a series that goes like this? 1 and then it gets smaller. 1/2 and then it gets smaller. 1/4. Can you tell what I'm multiplying by each time? I'm multiplying by 1/2 each time. This one, when you add it up, all the terms going to infinity, they don't add up to infinity. Isn't that a weird thing? If you keep adding, shouldn't your number keep getting bigger? If you keep getting bigger forever, shouldn't you eventually go to infinity? What do you think? Not if it's geometric. It will work for more than just a factor of 0.5. any factor that's less than 1, you can get, and this is the weird thing, it doesn't go to, the rule isn't just it doesn't go to infinity. The rule is you can find the exact answer. Even though you're going to add up infinite little, tiny little pieces, you can find out exactly what it comes out to. And they know the answer isn't just as simple as, well, you always get 2 or something like that. Nope. Depends on what you're starting with. What if you start with 3? And then you go down to 1/3 and 1/9 and whatever. There's a way to add these up, and the weird thing is an infinite number of little pieces can add up to something finite, like 2.5 or whatever. I'm not going to tell you the answer for this. I'm just going to tell you that it can be done and let that bother you a little bit. There's something similar that I like to explore like that, and that is that 0.5 repeating. Would you agree that that's 5/9? Did you guys know that? Okay. 0.6 repeating. Do you know what that's 6/9, also known as 2/3? You with me so far? All right. 0.7 repeating is 7/9. 0.8 repeating is 8/9. So what's 0.9 repeating? It is. Try it. 0.9 repeating? Wait a minute. If I follow this pattern, it should be 9/9. Do you think it just stops working on that one part? Like every other thing before it worked and then all of a sudden it stops working? How about this? 1/3, 0.3 repeating. With me so far? What's 2/3? 0.6 repeating. Oops. 6, 6, 6, dot, dot, dot. Add them together. 1/3 plus 2/3, 3/3 is, I'll just keep adding until you tell me stop. Because apparently 3/3 is 0.9 repeating. 0.9 repeating isn't just close to 1. So then I think a lot of you are like, okay, so you're saying it rounds to 1. It doesn't round to 1. It is 1. He's trying to prove it wasn't 1. Usually the argument is this, that it's 0.9 repeating. 0.9 repeating isn't quite 1. It's like some tiny little bit that left that's not quite 1. Do you get? That's kind of what it feels like it should be. But how small is that little tiny bit? Infinitely small. What's infinitely small known as? 0. So how far away is it from 1? 0 away from 1. And I'm not just rounding, though. See, it's not just really close to 1. It is 1. All right, one more proof for you. See if I do anything wrong here. See if I'm lying to you in any way. If I say n is 0.9 repeating, can I do that? Is that legal to say that? Okay. Wait a second. Let me finish this. And if I subtract, no, how about I can subtract anything I want from both sides, right? Or I can multiply by anything I want, right? So I'm going to multiply by 10 on both sides. Should be nothing wrong with that. What's n times 10? 10n. What's 0.9 repeating times 10? 9.9 repeating. Nothing weird yet. So if I can multiply by something on both sides, I can also subtract anything I want from both sides. So I'm going to subtract n from both sides. N. What's 10n minus n? 9n, right? And that's 9.9 repeating minus n. That's a little bit messy. Well, actually, since n is 0.9 repeating, then do you get it's just 9? Divide by 9 on both sides. What's the answer? So 0.9 repeating isn't just close to 1. It isn't like its limit approaches 1. It is 1. I can, but since they're the same thing, this is that, then I can subtract n here, and I can subtract 0.9 repeating there, because they're the exact same thing. All right, so anyway, I know by this time in the day when you don't have any food and whatever, it's probably not the best time ever to hit you with a weird brain bender, but it's just a fact. 0.9 repeating is equal to 1. And it's one of my favorite things to show kids because it makes them say, whoa, I guess there's more to this math than I thought, because I thought I understood everything, but that doesn't make sense to me. All right, to me, I think something similar that you may not be even comprehending how weird it is if I take 2, and then I take half of that as 1, and then I take half of that as 1/2, and I take half of that as 1/4, and I do that forever. Shouldn't I be adding a little bit forever and never even get the answer? But actually, you do. You can get that answer. Obviously, it's bigger than 2, right? Because if I add 2 plus 1, I get 3. It's bigger than 3.5 because you have the 3.5 and you add the 1/4. So, well, what is it? Well, I can show you how to figure it out, and you can know exactly what it adds up to. It adds up to a nice whole number. All right. So I shouldn't even say whole number. It adds up to a knowable number. It could be like 4 1/4, but I'll show you the pattern. All right, your homework for tonight. Let's get there, and I'll do the first couple with you. The first one you see is called classwork. That is not homework. That's classwork. That's like where you say, oh, okay, I want the first 4 terms. So all you do is start with 0, because that's what they said to start with, and then go things that are bigger than that. If I start with 0, I stick in 2 to the 0 is 1, 1 minus 0, comma. Then I'm going to put in the next logical thing that's bigger than 0, 1. 2 to the 1 is 2, minus 1 is 1, 0, comma, 1, comma. And then you make your list of terms. I'm going to just keep going a little bit further. 2 squared is 4, minus 1 is 3. Do you get that this one went up by 1 and this one went up by 2? Did I add something each time? Make it arithmetic? No. Did I multiply by something each time? No. So this isn't arithmetic or geometric. I want you to get that there's something called neither. There are sequences that go up or down, but not always by the same thing, and therefore they're not arithmetic and they're not geometric. So I'll just do one more in this series. I put in 0 to get this. I put in 1 to get this. I put in 2 to get that. Now I'm going to put in 3. 2 to the 3rd is 8, minus 1 is 7. So this is one that's an example of a neither. It's not arithmetic, it's not geometric. And all you'd have to do is write down the first few terms. We're going to do that when we actually hit the homework. Find the one that's got a fade from blue to red. And it says day 1, big on the top there. That's actually the homework. It's not the classwork, it's the homework. We will start it in class, of course. Now, this is one of the few assignments where the first few questions that you hit are actually the hardest questions of the whole homework assignment. And it's mostly just because you got to think about what they're trying to tell you. By saying this, they told you something important. If your goal is to list the first 4 terms, which I don't know if that's written in your homework, is it? Okay, write it in. List first 4 terms. That's your goal on this page. Then, what's the first term? By saying this, they told you what the first term is. And it's not 1. A sub 1. What is A sub 1? 117. That's the first term. Because it says A sub 1 is 117. And you have to know these are all A sub things because of the context of the question. And the next one, they're all going to be F sub things, but that's for later. 117 is our first. What's our next term? Use that big brain. This is telling you I take any nth term, and I can take the term, what is this, the term in front of it or the term after it or something? And it tells you how to make the next term. So again, I'm going to circle the important part. Right here, it's telling you how to make the next term. Who knows what they think the answer is? I don't need some decimal for it. Yes? Yep. Because why? 117 is our first term. And to get our, what is this? The term after the first term. See, that's what this means. That means the one after it. To get the one after it, you put 1 over your first term. So now do you have the pattern? You take, to get your next term, you take the term in front of that, and you do what to it? 1 over it. But instead of writing 1 over 117, you should know what that means. What is 1 over 117? Yes? Nope. Not as complicated as you think. It's just 117. Because when you put 1 over something, you're just saying to flip it? You put 1 over something, you're just saying, hey, take this and flip it. Well, take that and flip it. What do you get? 117. This is one of the weirdest series you've ever seen. And then, well, now that you kind of got the pattern, it's not going to be that hard. What do? 1 over 117 again. Because they're telling us in this, it's a complicated way to say it, but they're telling you to just put 1 over it to get the next term. If I had 2/3 and I put 1 over it, do you get that would change to 3 over 2? If you don't know that, it's because 1 over 1 divided by 2/3 is really 1 over 1 times by 3/2, which is 3/2. So basically, 1 over something flips it. See how it was 2/3? We put 1 over it, and then it flipped it. All right, the next one also is kind of a brain teaser. It's not impossible. It's not at all. But I'll give you this. First 4 terms, well, this is your first one, and that's your second one. 1, comma, 1, comma, and then it tells you how to get the next terms. This is directions. This is how we get the next few terms. These mean things like the term in front of it, or the term behind it, or the term 2 in front of it, or the term that's 2 spots behind it. And this is, there's only one sequence in the world that starts with 1, comma, 1 that I know of. So you just got the fancy way of saying a certain sequence. Hopefully you can figure out what the first 4 terms of that are. I'm not going to tell you. So it's weird. Challenge problems at the beginning now. Kind of like the mullet. Instead of business in the front, party in the back, this is the party in the front. Easy ones in the back here. All right. Number 14. Oh, okay. If you want to consider that business in the front, like the really hard business, like okay, I'll buy that. So it's just a mullet, not just not an inverse mullet. Okay. Anyway, look at number 14. Notice it doesn't tell you to do this, but I'm going to strongly recommend that you find the first 3 terms. Because when I tell you that the first 3 terms of this are like 1, 5, and then 7, you'll be like, well, you're just adding 3 each time. Yeah, it's that easy once you see the first 3 terms. Okay, so what are the first 3 terms of this? Nope. when I put in the first thing, which is, what do I put in first? 1, it tells me that 1 is where you start. I'm going to put in a 1, and what do I get? -2 is the first term in my sequence. Then I'm going to put in the next thing after 1, which is 2, and then it's 6 minus 5 is 1. And do you get what's going on here? Well, if you don't, then find the third one. What do you get for the third one when you put in 3? 9 minus 5 is 4. And now with each 3 terms in a row, you probably can say, oh, it's just adding 3 each time. So now can you answer their question? Is it arithmetic, geometric, or neither? Apparently it's arithmetic. Because the first 3 terms, all I have to do is add 3 each time. This is the first term. Would you agree with that? Then you go to that by doing what? Adding 3. So if it is arithmetic, find the common difference. Well, it's really not that hard. Just don't forget that part. It is arithmetic. So what's the common difference? Yep. And we call it D for difference. And you say D equals 3. And now you're done with that one. For the next one, they tell you to start with 1, so you stick a 1 in, and that'll tell you the first term. I encourage you to find the first 3 terms, and then it'll be a lot easier once you know, oh, it's just 6, 8, 10. Oh my gosh, it's adding 2 each time. It's arithmetic, whatever it is. What if it's not arithmetic and it's not geometric? Then what is it? Neither. Or neither. All right. This, do you remember me telling you those formulas? That's where you use those. If you wrote them down somewhere, you'll be happy you did. Okay. Is this the arithmetic kind? Yeah, it's going up 2 each time. So I got that formula, and I just use that formula. This is the kind where it's multiplying by 1/2 each time. That's geometric, so I got to use that formula. All right, moving on. Find a sequence that's both arithmetic and geometric. I'll give you a clue. Then it's not arithmetic or geometric, and therefore it's neither. You saw a couple examples of neithers before. So find your own neither. You cannot just do random numbers. 2, 8, 17, it's neither. No, you got to be able to tell me what is your little formula for getting it. And hint, they gave you some before that were like that were neithers. I'm not going to go all the way back to them. All right. So, again, don't just make up random numbers. The last thing we got to do is talk over this. And I think this is well worth talking over. So even because tonight's homework is pretty easy, I'm going to ask you to shut your iPads now. And the last question I'll do with you. Because the last question is just discuss. So we're going to discuss this. So you're going to be disgusting in a moment. Disgusting it with me. Ready? All right, so you're going to discuss Malthus. Who knows anything about Malthus? You ever heard of him? Well, so what do you say? Generally. Don't give me this quote off the screen, but generally, what do you say? So basically, the population would start to, like, starve to death because there wouldn't be enough food. Okay. And here's exactly what he said, and what he said was math. He was a mathematician, really. He's wrong, it turns out, because we didn't all die. He picked a year, actually, that we would run out of, like, where we wouldn't have enough food to feed everybody. And you might think that that's the case, but we actually have extra food. We just can't get it to the people that need it. So sadly, right this minute, there are people starving to death. And it's just simply that we can't get the food to them that fast. And you might think, well, can't we just airdrop it in there? They've done studies on these kinds of things. You can't just go and drop food in. Then you're going to cause it to be the rule of the strongest survive, and the strongest will grab the food and hoard it and keep it away from the people who really need it. So you can't just drop the food in there. And you know what? The first thing when they started dropping food in Somalia, you know what the first thing that happened? People weren't used to getting food drops. They tried to catch it. Killed tons of people. And or hurt them really badly. Yes. Serious. And yes, the warlords took it. But the very first time when they just thought, we'll just drop it in there. We don't have to have anybody there or anything. We'll just drop it. And they dropped it, and the people were like, oh, there's food coming down. What is this? And they had a ton of people get injured from getting hit by the stuff. So the next time they tried just dropping it, and if you just, like, before, actually they had given them warning, so they were all standing out in the field like, hey, they're going to drop food, because they had dropped leaflets ahead of time saying, we're going to drop your food at this time. And then they found out that the people will gather in a giant mob waiting for the food. That's not good. And get crushed by the food when it hits. That's not good. So then they tried dropping the food in and they random time, and then just having them find out that, oh my gosh, did you hear? There's tons of food out in the field. And so then everybody run in. But then the strongest survive again. The strongest are going to like hoard it because they know that their whole family's starving to death, and they're going to like, I want all of this, and then they're going to start fighting the other people, and the poor people that are really weak and like, dying from starvation aren't going to get the food, and the strong people are going to get the food, and that doesn't work either. So anyway, it's complicated. So was Malthus right? He really wasn't, but he had an interesting theory that I can't even argue with. Population increases in a geometrical ratio. Do you get, if I have a mom and dad, so to speak, a family of 2, they can produce a whole bunch of kids. Could be like 16 or whatever. So 2 can turn into 16. And you get, if we have 2 sets of families like that, just so that you don't have to have inbreeding, okay, we're going to have this family and then another family over here that started with 2, and then they have 10 kids, that all of a sudden the kids can have kids, and holy crap, you can have tons of people after just starting with like 4. Okay, you get that? That's geometric. It can go up really fast. So he says population growth is geometric, but subsistence, as in food, increases in arithmetical ratio. So like if you want to grow more grain, you want twice as much grain, got to plant twice as many fields. You get what I'm saying? It's simple. It's just you got to have twice as much. That's arithmetic. Adding, I need twice as much. I got to add another twice as many fields. And he said that a straight line growth like that is going to get beat by geometric every time. And I can't argue with that either, except that there are some flaws that he didn't think about. So what turned out to be different than he thought? Yes?
Agricultural advantages were much better.
So they weren't arithmetic.
No,
So the food growth, just picture this. In Minnesota, have you guys driven past a farm? All right. Those farmers, imagine at the end of the year, they just put all their crop in a giant pile on a cement floor. And actually, honestly, that's what they do. They just truck it off before it gets to be a giant, giant pile. So at the end of the year, they have this giant pile of grain. The thing that's really cool is over your lifetimes, the amount that they can produce has gone up dramatically. If you go back far enough, the amount that they can produce is now like 8 times as much off the same farm, same size number of acres. They can get like 8 times as much food. It's just crazy. Every year it's going up too. Like this year it went up to around, in the best farms, it's like running 300 bushels per acre, where it might have only been like 40 bushels per acre a long time ago. So they're getting more and more and more out of the same field. He didn't picture that. He didn't factor that in. So what else didn't he factor in? He said unchecked population growth. Does every family have like 19 kids? That would be unchecked population growth, but we check it. Yes? China's one-child policy is a great example of that. That's a little different than what we do. We let people decide for themselves. They actually said you will not have more than 1 kid. And there was even plenty of instances of reports of forced abortions where a woman would have another baby on the way, and then they would force her to have an abortion. Whether or not you believe abortion is okay, forcing somebody to have an abortion, terrible. Hard to imagine that. But I'm not China, and I didn't have to deal with what they were having to deal with, so I don't want to judge them other than they decided for themselves that's a bad idea. And so they stopped the one-child policy, not necessarily because they didn't like the fact that it was keeping the population down, but because their population was getting really old, and there weren't that many young people to take care of them. So pretty soon, if you have a ratio of like 8 old people to every 1 young person who's working and trying to feed them, that can't work, right? So population growth has been checked, and the food supply has gone geometric. Will it last forever? We don't know. All right. That's all I got for you for today.